All right, so we have the communications going. So now what we actually want to do on top of this is let's add peripheral. We have this wonderful memory. So this is like our RAM / where the program will live. We have this reset. We have this debug module, which is like the JTAG. However, we don't have an actual way to communicate to the outside world. So what we actually want to do is we want to add a UART interface. So I'm going to do add IP up here, and then we're going to select UART. All right, looks good. So what we're going to do is we're going to create an application project. For that, let's just call it MB Hello World for Microblaze Hello World. Okay. So hopefully it's imported. So the last thing is we're just going to run Hello World. So it'll instantiate everything for us. So you should be able to just click finish. And that's it. Just to make sure it's actually executing our code, let's go to this hello world.c. And so it says like hello world /r/n. Let's change it to I has Microblaze. So that should work. And if everything worked, if we open up PicoCom, you should get I has Microblaze. So the boot process flowchart. So this is super useful to look at. Okay. So this is going to explain how the system boots. Up here, it checks CRP enabled first. So it even says that in the document. So this is going to be the critical thing. So it checks CRP enabled at the very beginning, and then that's it. Okay, that's going to be like the vulnerability that we're going to exploit. So it checks this value once during boot up, and that's it. And then everything else is based off of the value that are read there. And now, how does code read protection work? So let me zoom in. Let's do full screen, Dmitry, just to get the gravity, how serious this situation is. Okay, just so you can understand how stupid this implementation is. Okay. So this is a mechanism to enable different levels of security. So how does it work? So when CRP is needed, you program a specific pattern in flash location 2FC. So let's take a look at these secure values that you have to program into the flash. Hex 1234567 hex 876543221. And then this is the one where they got really fancy. It's 43218765. Okay, so this other value, this other secure value. So may I remind you that this mode is called no ISP. Okay, are you ready? I should check if everyone's sitting down, but I assume you are. Okay, so not very secure values by NXP. What's happening is it's checking the read protection value once. So if we can manage to corrupt this value, we win. We won the lottery. So we'll be able to defeat the security on this chip. For example, we can do R04 as a command. So this is the read command, and we're saying read address 0 and read 4 bytes. So R04. And you'll get something like this. So right here, the R got overridden by a 0. So what's the 0? Well, the 0 happens to be, it's a status code. It means command succeeded. I get the okay. So now let me do R04. Wah wah, 19. We got a 19, guys. So let's say we created the most simple circuit possible, which would be like cascading inverters, okay? So how far would the signal propagate in like a given unit of time? Well, let's say the voltage is 3.3 volts. Well, the signal might propagate to here, okay? So then let's say the signal is 1.8 volts, okay? It won't propagate the same distance, right? So what does this have to do with? Well, one of the biggest parameters that you affect with voltage is the transistor switching times. So the multiplexer has a select, and it has a 1 and a 0 and an A and a B. Okay. So if select is 1, then we output A. If select is 0, then we output B. So basically we're going to check. So if the first byte is okay, then we're going to check the next byte, then the next byte, then the next byte. So basically what we need is a state machine consisting out of 4 states. So we already have RX valid. So let's just check the data. So if it's a null byte, then we can continue to the next state. So then what happens right here? Well, we actually take whatever byte we got. So then we're going to take the least significant bit. 720. So we're going to take in the width. And when this happens, we'll set glitch enable to 1. So here comes the data. Here it comes. Then I want to see a reset, and offset from the reset, I want to see the VCC select. So they have these pads, and what these are shunt pads. So they're actually there so that we can sever them, put a resistor there, and then measure the current that goes through the system. So what I'm going to do is, if I actually cut through here, I will have separated the chip from the power supply and everything else on the board. So now let's sever that connection. So I'm literally just going to take the knife, and people ask me how do I know that the connection's gone? And it's like, go until you hear a crunch. So I heard a crunch. I heard another crunch. I also removed a capacitor here, and I've permanently soldered P03 in. The greatest thing that came out in 2018. Does anyone know what it is? Okay, let me show you, but only because I like you guys. Is this, and so what they are DC step-down power supplies. So what you can do is you can grab a power supply, plug it into there, and then you're good to go. The blue signal is the reset, so you can see it's going from 1 to 0, and the yellow signal is the glitch, so everything's working. All right, 1.55. So you can see we're even running it below 1.6 volts. It's significantly lower than 1.6 volts. So I mean, this is outside of what the manufacturer claims this board can run at. So I would say confidence is high. Okay, so what just happened? So it succeeded to read from flash. So it succeeded to read 04. Okay. So let's check. I can do R 200, 300, or 400, and it'll read some data, etc.